Besides the primary reason of reducing friction, there are secondary reasons for having a lubricant within the engine. Even if the engine was kept scrupulously clean, there will always be small amounts of dirt or impurities that find their way inside it. That dirt must be removed from the oil before it can cause damage to bearings or block small oil passageways within the engine. The oil keeps the interior of the engine clean by carrying any contaminants in suspension in the lubricant to the oil filter, where they're removed. The majority of the bearings within the engine are manufactured from steel, a metal which would soon oxidize itself if it were not prevented from doing so by a liberal coating of oil. Thus the lubricant also minimizes corrosion inside the engine. The bearing surfaces in the engine, particularly those towards the turbines, must be cooled if they are to be able to withstand the constant heat stresses imposed upon them. The lubricant is used to take the heat away from the bearing surfaces and transfer it to the oil cooler, where it's dissipated into the atmosphere. A further task of the lubricating oil is that of being a hydraulic fluid. For instance, in some turboprop engines, the control of the pitch of the propeller blades is achieved by using the engine lubricating oil to operate the pitch change mechanism. Most gas turbine engines use a self-contained recirculatory lubrication system in which the oil is distributed around the engine and returned to the oil tank by pumps. There are two basic recirculatory systems which we'll investigate here. They are the pressure relief valve system and the full flow system. The pressure relief valve, which gives its name to this type of lubricating system, is situated in parallel with the oil pressure pump. It limits the pump outlet pressure by diverting any excess volume back to the inlet of the pump, thus controlling the flow of oil to the bearing chambers. The engine oil pressure is restricted to a value which the engine designer considers correct for all conditions that the engine might encounter. The pressure relief valve will begin to relieve pressure at the value which is generated by the oil pressure pump at engine idling speed. As a consequence, the pressure relief valve theoretically maintains a constant pressure over the whole of the engine's speed and oil temperature ranges. This diagram shows the basic components required in the pressure relief valve lubrication system of a turboprop engine. The oil is drawn to the pressure pump through a suction filter. The suction filter protects the pressure pump from damage should any debris enter the tank. The oil pressure pump is contained within an oil pump pack. The oil pump pack contains one pressure pump and several scavenge pumps. Having several scavenge pumps ensures that the lubrication system remains a dry sump system. From the pressure pump, the oil is passed through the pressure filter, which removes any small particles which may block the feed jets. The oil then flows to the pressure relief valve, which maintains the oil pressure to the feed jets in the bearing chambers constant. The oil is passed to the feed jets through internal drillings and external oil pipes. In this particular engine, the hollow interior of the compressor turbine shaft is used to transfer oil from the front of the engine, where it's used in the pitch control mechanism, all the way through to the rear of the engine, where it's used to lubricate and cool the turbine bearings. The torque meter pump shown in this diagram is used to boost engine oil pressure to a figure which is considerably higher than normal system pressure. In some turboprop engines, the torque meter pump output can be as high as 600 pounds per square inch. Torque meter pressure is utilized to balance the axial thrust of the helically cut gears within the propeller reduction gear. The axial thrust is proportional to engine power output. When the oil has completed its task of lubricating, cooling, cleaning and acting as a hydraulic medium, it falls into collecting trays or compartments from where it makes its way to the scavenge pumps. The scavenge pumps push the oil through an air-cooled oil cooler, where the heat is dissipated into the atmosphere. From the oil cooler, the oil travels to the de-aerator tray, where any air bubbles, which will have been formed in the oil, escape, and the oil falls to the oil tank, which in this case is contained around the engine intake. Any air pressure which has been built up within the engine lubrication system, through leakage from seals or from the de-aerator tray, must be allowed to escape. If the air pressure was just vented to atmosphere, then any oil mist contained within it will pass to atmosphere also. Thus the oil contents would quickly diminish. To prevent any loss of oil occurring in this manner, the oil mist is vented via a centrifugal breather, which is fitted to and driven by the accessory gearbox. The full-flow lubrication system achieves the required oil flow to the engine throughout its entire speed range by allowing the oil pressure pump to supply the oil feed jets directly, without the use of a pressure relief valve. Using this type of system allows the use of smaller pressure and scavenge pumps, since the volume of oil passed by them is less than that which is passed by the pumps in the pressure relief valve system. This discrepancy in the volume of oil used in each of the two systems exists because of the large amount of oil which is spilled back, either to the oil tank or the inlet of the pressure pump, in the pressure relief valve lubrication system at high engine speed, whereas no excess pressure is generated in the full flow system. The pressure pump picks up oil from the oil tank through a suction filter. The high pressure oil generated by the high pressure pump passes through a pressure filter to the distribution galleries. Fitted across the pressure filter is an oil differential pressure switch. The oil differential pressure switch will give a warning of filter blockage. This warning is usually indicated at the ground crew servicing panel, and is sometimes duplicated by a warning light on the flight deck. The upper portion of the oil gallery transfers the oil to an oil pressure transmitter and low oil pressure warning switch. These items are used primarily to give warning in the cockpit of malfunctions in the oil system. Other parameters indicated in the cockpit are those of oil quantity and oil temperature, the latter being measured as the oil leaves the oil cooler. A tapping from the upper portion of the gallery transfers oil to lubricate all of the bearings in the accessory drive gearbox. The lower portion of the gallery is used to transfer oil to the bearings which support all of the compressor spools. The bearings are lubricated by oil jets, which are positioned very close to the bearings. This minimizes the possibility of the oil being deflected from its target by local turbulence. Thread-type filters are fitted in the oil supply line just before the oil jets. Thread-type filters perform the function of a last-chance filter, removing any debris which may have managed to pass through the main pressure filter. In a similar manner to the pressure relief valve system, when the oil has completed its tasks, it's collected by scavenge pumps. Prior to the oil reaching the scavenge pump, it passes over a chip detector and through a suction filter. The scavenge pumps pass the oil to the oil cooling system. This engine utilizes two types of oil cooler, a fuel-cooled oil cooler and an air-cooled oil cooler. Normally the fuel-cooled oil cooler is sufficient to cool the oil on its own, but in the event that it proves inadequate, a valve opens automatically and brings the air-cooled oil cooler into operation as well. We mentioned earlier that air pressure escaping from seals cannot be allowed to build up within the engine. In this engine, air pressure within the engine is vented through the hollow shaft of the drive between the intermediate gearbox and the external gearbox, leaving the external gearbox via the centrifugal breather. The oil tank is normally a separate unit mounted on the side of the engine, although it can be part of the engine intake, or even an integral part of the accessory drive unit. Whatever form the oil tank takes, it must incorporate provision for filling, either by gravity and/or more normally from a pressure source. There must also be some method of determining the contents of the tank, either by a sight glass or by a dipstick. Sometimes both methods are used. A de-aerator tray removes air bubbles from the oil as it flows back into the tank. Gear-type pumps, which consist of a pair of intermeshing steel gears located within a close-fitting aluminium housing, are the normal method of delivering and retrieving oil in a recirculatory system. This diagram shows a gear-type oil pump. When the gears are rotated, oil is drawn into the pump, carried round by the teeth, and delivered at the outlet. The oil pumps, both pressure and scavenge, are fitted on the accessory housing. The oil pumps are fitted within an oil pump pack, which consists normally of one pressure pump and perhaps as many as 7 scavenge pumps. Having several scavenge pumps ensures that the lubrication system remains a dry sump system. Oil coolers can be either air-cooled or fuel-cooled. We've seen that some engines use both systems. If an engine does use both air and fuel to cool the oil temperature can be monitored electronically and the air cooler switched in only when it's deemed necessary. The oil temperature is maintained at a value which helps to improve the thermal efficiency of the engine. Whether it is fuel-cooled or air-cooled, the oil cooler is basically a radiator which exchanges heat from one medium to another. The oil cooler consists of a matrix assembly, which is partitioned by baffle plates. The baffle plates ensure that the oil takes the longest path through the matrix, and it thus gains maximum benefit from the cooling effect of the fuel flowing through the tubes within the matrix. The fuel-cooled oil cooler has a double benefit. The fuel in the aircraft wing tanks is invariably very cold and requires warming up before it gets to the fuel filter. The oil is hot and requires cooling. This device allows both requirements to be carried out within it, a rare chance of achieving 2 for the price of 1. Incorporated in the fuel-cooled oil cooler is an oil bypass valve, which is fitted across the oil inlet and outlet. If the oil cooler becomes blocked, when the oil pressure in the cooler inlet zone reaches a predetermined value, the oil bypass valve communicates directly between the oil inlet and the oil outlet. This will prevent oil starvation in the engine and will also preclude the chance of excess oil pressure damaging the relatively fragile matrix assembly. In the event that damage to the oil cooler matrix does occur, fuel is prevented from entering the oil system by the oil pressure being kept at a value higher than the fuel pressure. This is done by a pressure-maintaining valve located in the oil feed line to the cooler. Thus the oil will leak into the fuel system rather than the other way round. Chip detectors, which are permanent magnet plugs, are situated in some of the scavenge lines to collect ferrous material from the oil as it returns to the scavenge pumps. The chip detector is retained in the pipeline by a bayonet fitting within a self-sealing housing. The fact that the valve housing is self-sealing means that the detector can be removed without any loss of oil. Contamination of the magnet by iron filings is illustrated here. This type of contamination can be taken as evidence of impending failure in the bearing chamber, which is being monitored by that particular chip detector. We've already stated that to prevent excessive air pressure within the accessory drive unit and the bearing chambers, the interior of the engine must be vented to atmosphere. Airborne oil droplets in the air within the engine form an oil mist which, if it was allowed to escape unhindered, would rapidly deplete the engine oil contents. The oil mist is vented to the accessory drive unit, where it must pass through the centrifugal breather before reaching the atmosphere. The centrifugal breather is rotated at high speed and as the oil mist enters, it's thrown outwards by centrifugal force. Around the inside periphery are de-aerator segments. The oil is separated from the air and is eventually flung back into the accessory drive unit to be picked up by a scavenge pump. The air, having less inertia, makes its way out of the centre of the rotating portion of the breather to atmosphere, having had all of the oil removed from it. Thus the centrifugal breather minimises oil loss in the gas turbine engine. To facilitate the oil's task of cleaning, a number of filters and strainers are positioned within the lubrication system. The filters and strainers prevent debris and foreign matter from being continuously circulated around with the oil. As we described earlier, the oil is drawn from the oil tank through a suction filter before it goes into the pressure pump. The suction filter takes the form of a coarse strainer, which prevents debris being drawn into the pump and damaging it. At the outlet of the pressure pump, a pressure filter is fitted. This is a very fine mesh filter, which will retain any small particles which might block the oil feed jets. Thread-type filters perform the function of a last chance filter immediately prior to the oil jets. Each return oil line contains a scavenge filter just downstream of the magnetic chip detector. These scavenge filters will collect any debris returning from the bearing chambers. Both pressure and scavenge filters are constructed in a tubular form from either a very finely woven wire cloth or resin impregnated with fibres. Some filters may have a differential pressure switch fitted across them, or alternatively they may be fitted with a pop-up indicator, a small button which can be seen protruding from the filter casing to give a visual warning of a partially blocked filter. Gas turbine engine oils must have a high enough viscosity for good load carrying capacity, but they must also have a sufficiently low viscosity to ensure a good flow of oil at low temperatures, as would be the case, for instance, when starting after a prolonged cold soak. Early gas turbine engines used the same oils as had been used in petrol engines for years. These oils were mineral-based. It was found that under the higher temperatures and speeds at which gas turbine engines operated, mineral oils burnt, scummed and oxidized. To attain the properties mentioned at the beginning of this lesson, synthetic oils were developed. Synthetic oils have the following qualities: low volatility to prevent evaporation at high altitudes, a high flash point which will prevent the lubricant igniting at high temperature points within the engine, such as at the turbine bearings, a high film strength which gives the oil molecules the ability to stick together under compression loads and adhere to surfaces under centrifugal loads, a wide temperature range. Most gas turbine lubricating oils have a temperature range of minus 45 degrees Celsius to plus 115 degrees Celsius. A low viscosity, which increases the ability of the oil to flow under low temperature conditions. A high viscosity index, which is an indication of how well the oil retains its viscosity when heated to its operating temperature. Low viscosity oils can be used in gas turbine engines because of the absence of reciprocating parts and heavy-duty gearing. However, turboprop engines, which have reduction gears and propeller pitch change mechanisms, require a slightly higher viscosity oil. Gas turbine engines are invariably dry sump engines. The oil level of a dry sump engine should be checked immediately after engine shutdown, or at least within a specified time after engine shutdown. This concludes the lesson on lubrication.